Okay, and start this. Okay, so today more NP completeness, and then there'll be even more NP completeness on Wednesday. The stuff on Wednesday will be sort of hard but fun. So the stuff on NP, the stuff on Wednesday will be like stuff that you're not supposed to see on. Nobody wants to say it's actually cooler in my apartment than it is out there. I think I should try going out, but I have this paper due. Wait, so I'm recording there. I'm recording there. Okay. So I realized that I should have actually been teaching NP completeness a different way. So I started on Wednesday. I did talk a bit about decision problems versus optimization, or versus search problems or optimization problems. The decision problem is just you say yes or no, like is there a clique of size k? A decision problem, you actually have to find something. But you can, I said like, okay, you can turn a search problem. If you can solve the decision problem, you can solve the search problem by like multiple calls to the algorithm that solves the decision problem. Okay, so we're just considering search problem, decision problems. So what I could have told you is, I was thinking of how I should put it in the lecture notes, which I'm afraid are still not out. Okay, changing the chat. So what I could have said is, right, we had clique. We all know this graph. We had independent set. We have vertex cover, and we saw that in polytime, you can turn an instance of clique into an instance of independent set, such that the instance of clique can be something that has a solution. And it is yes, if and only if the independent set is yes. This is recording. That is recording. Just okay, and so because we've talked about polynomials are a ring. So the other thing, polynomials are closed under composition. So if you blow this, if you take an instance and you process in polytime, you blow it up by a most polynomial factor. So that means you still end up with something which is polynomial. And then if you run in time on polynomial on this new instance, it's still polynomial in what you started with, right? So it doesn't matter if I have to do a constant number of steps. This is a constant number of compositions of polynomials. I'm still ending up with. So then we had okay, we had 3 call. Did you see planar 3 colorability in the tutorial? The reduction of 3 colorability to planar 3 colorability. So if this is planar 3 call, then obviously you can turn planar 3 call into 3 call. Did you see that you can turn 3 call into planar 3 call with this sort of diamond shaped gadget that if you have 2 edges which are crossing and you want to, not have them crossing, so the thing is planar, you plug this sort of diamond in and it lets the edges, it sort of moves the stuff, it moves the stuff across. So I forget, but you'll see it has like a vertex here and a vertex here and a vertex here and a vertex here. And it's got like some more stuff in here, and these are connected and these, and so it looks sort of like this. And you plug it in and you say, okay, if this is green, this has to be green. If this is red, this has to be red. So it lets you cross. Did you see this? I think you were supposed to. I'm not sure if you were supposed to. Yes, cool. Okay. So we did planar 3 call to 3 call. On Friday, you may also have seen ham path. So sats to ham path. but it'll be in the lecture notes. So, so there's this 3 sat. And on Wednesday, we saw that you could turn 3 sat into independent set. Normally you see 3 sat into clique, but it's just easier to draw if it's into independent set. So we also saw that you could turn, I guess, independent set into, well, you could, I think we maybe saw clique. You could turn clique into 3 sat. Right, so if somebody gives you an instance of clique, remember what you would do. Actually, sorry, not into 3 sat. There's this other problem, sat. We did see clique into sat. Okay, so this is going to be key here. And I asked you to believe me that you can turn sat into 3 sat. Questions? Okay, so do you remember that we saw that you can turn clique into sat? That is, if somebody gives you a graph and says, does it have a clique of size k? You can write a formula such that the formula is true if and only if the graph has a clique of size k, and the formula basically says the graph has a clique of size k, right? So what you're going to have is, if you have a, okay, so does this have a clique of size, well, 3, let's say. Let's say this is V1, V2, V3. Well, let's take this out. So, okay, does this have a clique of size? Does this have a clique of size 4? This 1, 2, 3, and this 1, 2, 3. Yes. So okay. Does this have a clique of size 4? So what we're going to do is have this variable. We're going to have x1 says that v1 s1 x1 says v1 is in the clique. So this is how to think about it. It doesn't actually say anything like this, but you know, so in general, you say xi says vi is in the clique. And then you go through and you say, okay, well, it can't be the case, so it's not v5 and v3, right? Because there's this edge missing. So you say, okay, that's not true. So for each edge that's missing, you go through and say, okay, the endpoints of these missing edges cannot both be in the clique. They can't both be true. And then what you need to say is, okay, we need to write a formula that says at least 4 of these things are true. And that's the tricky part. Right? You have to write something. And to do this, you use these variables, these sort of counter variables. I forget what, maybe I call them y, but you say Cij says at least j of x1, xi are true. Right, so how do you compute this? Well, you say, okay, Cij is only true if either, okay, so C11, let's see, C11 is only true if x1 is true, right? Because the only way you can get at least one of things up to x1 is if this is true. And then Cij, you say, okay, and other ones, C1, okay, this is like dynamic programming. C1K is false for K greater than 1. And then Cij is only true if either Ci minus 1, J minus 1, and Xi. Right? So this is saying if I can get if at least J of these things of x1 to xi minus 1 are true, fine, then I can get at least J of x1 to xi are true. And otherwise, like if I can get if I can get J minus 1 of them and xi is true, then I can get. Okay, so this is the only tricky thing. I can teleport now. That's kind of cool. Superhero? I'm a lag. Oh, no, that came after, didn't come after he's an alien. It came after probably a freeze frame issue. It's probably my internet. Okay, so we went through this. We saw how to turn clique into sat. We saw sort of the same thing for 3 colorability was a bit easier, where you could say, okay, given a graph, say that it's 3 colorable for every vertex, or we actually did 4 colorable. So 3 colorability from the beginning of the course, we knew that you could turn it into 4 colorability, and you could turn 4 colorability into 5 colorability by just appending by attaching this extra vertex. Oh, I forgot to start the timer. Ah, okay, so I have like 12 minutes. Okay. So I was doing that because I wanted you to get used to this idea that you can reduce stuff to sat. Like, given a problem, think about how to write a logical formula that says this problem is solvable. Okay. It doesn't, you don't solve the problem like this, right? You're just taking a formula. This formula is true. This formula is satisfiable if and only if this instance of a problem has a solution. This graph has a clique, this graph has a 3 coloring, whatever. Okay. The painful part about this is this kind of thing, like writing counting. Writing counting using formulas is a pain. Okay. Now, so we saw hem path. So hem path. And on Friday, I get you saw that 3sat reduces to ham path. Actually, maybe you saw that 3sat reduces to directed ham path, but directed ham path reduces to ham path. And how would you do? Okay, why did I draw this? Okay, because like if we actually wrote this out, you would get a formula, which I will do in the notes. You would get a formula that says that this has that's satisfiable if and only if this has a 4 clique, and we would actually see what the satisfying truth assignment which is x1 is true, x2 is true, x4 is true, x5 is true, and x3 is false. Okay, so ham path. How would you write a formula? Okay, how would you write a formula that says this graph has a Hamiltonian path? Well, what you would do, you use lots of variables, and you would say, okay, if there is a Hamiltonian path, so this means you get to start somewhere, and you walk around, you visit all the vertices, and you get to end somewhere else. Okay? Anybody still here? 16. Oh, that's not bad. Okay. So does anybody want to suggest how, okay. for the sake of time, I'm going to tell you how to do this. But this is the kind of thing that could show up on the next midterm or something like that. Actually, I sort of know what's going to be on the next. I haven't figured out exactly what's going to be on the next midterm, so this might show up. Okay, so what you would do is you come up with an x with a variable xij. So this variable xij says we visit vi as the jth vertex. So I'm going to say it's a walk. You start somewhere, you walk around, you visit all the vertices, and you finish. So it's the xi should be true if we visit vi as the jth vertex in the walk. Right? So we're going to have a big, how many of these things are we going to have? We're going to have like quadratically many of these xij's. For every I from 1 to n, and from every j from 1 to n, you have an xij. So x 4, 3 says we visit v4 third in the walk. Okay. Nobody actually does this except in like my class. Okay, because there's a reason for that, which we will see later in this class. Okay. So if you think about it, like, okay, what would you do? You would then write little formulas that say, okay, x not xij and xij prime for j not equal j prime. Okay, so you just go through and say, okay, if I visit it jth, I don't visit it another time. Okay, it's a Hamiltonian path. I go around and I only go around once. Okay, you also write little things that say, okay, not xi, j, and xi prime, j. For I not prime not equal prime. Okay, and this is saying if I visit vertex v4 third, then I'm not also visiting vertex v2 third, right? And then you have to have like little statements that say, okay, somebody gets visit. You have to say, okay, of all these guys, either v1 1 or v2 1, or you have to visit every vertex at least exactly once. So like, okay, either I visit vertex 1 first, or vertex 1 is second, or vertex 1 is third, or vertex 1 is fourth. And you still do that for all the vertices. And you also say, okay, and then you also have a big or that says somebody has to be visited third, right? So you have all this stuff, and maybe you can simplify it a bit. You have all these formulas. How many? Polynomially many. So you write this big formula, and you think about it like, yeah, okay, that is going to be true. That's going to be satisfiable. Sorry, not true. That's going to be satisfiable if and only if there's a way to pick these, to set some of these xij's true and some of the xij's false, such that you would actually have a Hamiltonian path. So you would take the statement of the problem, the Hamiltonian path problem, that says, okay, you're going to visit each vertex. You're only going to visit it once. So you're going to visit it's going to be a walk of n vertices. Every step in the walk, you have to be somewhere. You only go there once, blah, 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 blah. Oh, and the other thing, the key thing is you say if xij and okay. So you say not xij and xi prime j plus 1 for all of the edges that are missing. Okay, so for all of the pairs, I cannot go from V5 to V3. So if I'm visiting V5 second, then I'm not visiting V3 third. So for each of the missing edges, you go through and you say, okay, if you're visiting this one at I, then you're not visiting any of the things it's not adjacent to on the I plus first, in the I plus first position in the walk. Okay, do you see how to write? You know, you take this description, you're like, yeah, I did it. I could type it in, blah, blah, blah. People, anybody? You see this? You believe me? You could do this? Maybe. Okay. So we believe that hem path also reduces to sat. Okay. Now, considering just search problems, this stuff, oh yeah, 3 colorability, 3 sat. We turned 3 sat into 3 colorability. You remember I had that little gadget and and we said, okay, we had like true and false and base, and then we sort of built little circuits out of vertices and edges. And so we reduced 3 sat to 3 colorability so that given a formula, we drew a graph. So the graph had a 3 coloring if and only if the formula was satisfiable. 3 sats, the formula was satisfiable. And you can do the same thing. You can take 3 color, well, actually, you can take 4 colorability and reduce it to sat. Okay. So, and that's just writing out this. Every vertex has to be one of 4 colors. It's only one of the 4 colors. And for every edge, it's not true that the endpoints are the same colors. Blah, blah, blah. So this gets a bit wordy, but you could do this, right? It's fairly, like all of these problems, like if I asked you on an exam or something to write a formula that says vertex cover, you know, given an instance of vertex cover, a graph and a size k, and it's like, does this have a vertex cover of size k? You could write a formula that's satisfiable if and only if that graph had a vertex cover of size at most k, right? Again, you have to go through this annoying thing of saying the vertex cover has size at most k. How do you have to do this like annoying counting thing? But you could do this. So that was sort of on Wednesday. This thing, now, okay, remember, for every step you take, it's, you know, you're possibly blowing stuff up by polynomial factor, but polynomials compose of polynomials in a constant time. It doesn't, in a constant number of compositions, it doesn't matter. So all of these things can be turned into each other in polynomial time. So that means if one of them has a polynomial time solution, they all do. Because if you want to solve planar 3 colorability, and you know how to solve clique, what do? Well, planar 3 colorability is 3 colorability. Well, you could turn it into 4 colorability. You could turn it into a sat instance. And then, I haven't told you how to do this, but you could turn sat into a 3 sat instance. And then you could turn 3 sat into an independent sat, and then you can easily turn independent sat into clique. Okay, so this thing gets polynomially bigger. So you slow the thing down, but if you have a polynomial algorithm for clique, it means you can solve any of these things because they're all connected. You can get from any vertex to any other vertex. This is NP complete, okay? If a problem is a vertex, now there are lots of other things where you can get from this graph, you can get from anywhere to anywhere else. There are a lot of other vertices. All these NP complete problems, and they're all sort of equivalent. You see that if you could solve one of them, you could solve all of them. If you can't solve one of them, you can't solve any of them in polynomial time. Oh, by the way, this is super cool. At STOC, the Symposium on Theory of Computing last week, it's the 50th birthday of P versus NP. So Cook did this in 1971, and I forget if it was at STOC or it used to be called SWAT. switching and automata theory, which is now actually a different context called SWAT, but now it's called SWAT. What was SWAT is now called FOX. Start. Okay. Yes. No, I don't want to do that. I want to start a video. Okay, so the two things I really want to do today are, well, I want to do three things. I want to do this line. I want to do Cook's theorem, and I want to cover Turing machines. Okay, so we have like 50 minutes left. So hang in there. Okay, so this is something called the Satan transform. So so basically the Satan transform says that if you're given a formula, you can produce another formula, which is in conjunctive normal form, so CNF, which is satisfiable if and only if the original formula was satisfiable. And basically what you're going to do, exactly how to spell C. You need a formula. Somebody quickly type a formula into the chat box. This is probably the old marker. So if you had like, yeah, this is the old marker. If you had X and Y or not Y and Z. Something, okay, I'm just going to do something really small. Okay, so this is not in conjunctive normal form. Okay, and so this is not in conjunctive normal form. Conjunctive normal form is a bunch of disjunctions, so ors, and then it's all anded together. So it's only sort of got, it's just a bunch of clauses called ors and just anded together. So what you're going to do is you're going to view this as sort of a binary tree. So the first sort of thing, you have an and of Y and Z. And then you have an and Y and Z, and then you have a not, and then you have an or of this and Y, and then you have an and. So let's say the order. I mean, these things. I forget which way these associate. Do logical operations associate? Do you do this way or do you do it this way? Okay, well, this definitely happens first. Okay, so we're gonna say that, okay, we're gonna do this and first, and, okay, I'm gonna put the brackets in to make everything clear. And of X and Y, and then this is an or. Okay. So how are you going to do this? Well, for each of these things, you're going to put, you're going to have a W1, you're going to have a W2, you're going to have a W3, you're going to have a W4. Okay, and then what you do is you write W1 is true if and only if Y and Z. Okay, W2 is not W1. W3 if and only if X and Y. W4 if and only if W2 or W3. And so these things are all binary. And what you do if you, let's just do this one. So it's W1 is true if and only if. So you can go through and see that you can for any statement where it's like some variable, if and only if, some binary operation on two variables, then you can write that as in conjunctive normal form. Right? So this is going to be either, so, well, okay, it's not Hi, sorry about that. My internet is a bit flaky. Okay, you will believe me. You can take these and just turn them into conjunctive normal forms. So I think it's either this is true or one of these is false. So it's either, if this is false, so it's either this is false or one of these is false, and either this is true or one of these is true, right? Or something like that. Okay. It will be in the lections. Okay, so this is so given given a general any Boolean propositional Boolean formula. Yeah, I'm sorry it disappeared. Bye. Given any Boolean formula, you can sort of turn it into a CNF formula. Now it doesn't have to be 3 CNF, but if you go through the state and transform, then it turns out that the clauses are always at most 3 literals. And then if they're less than 3, you can always just sort of pad them by repeating one of the literals. It doesn't change anything. So you can actually go from sat to 3 sat. So that means that from any of these, you can turn it into an instance of 3 sat. Yeah, okay, not that. I think it's Russian, so it's a different alphabet, but I think there, or maybe this is with a Y. So yeah, it's not hard, but the idea is sort of to break this into to turn this into the tree, and then realize that for each of these, to view it as like a binary, to view it with a circuit with fan in 2, and then realize that for each gate, you can write that gate as CNF. Okay. And then at the end, what you do is you say, okay, W4 has to be true for this to be true. So you have a W4, and then you have all these statements saying this is equal to these are equal to these are equal to these, but you have these expressed in CNF. Okay. So now this Hooke's theorem. So are you starting to get a feeling that SAT is powerful? See, you start to, I was doing this because I wanted you to feel like, yeah, if I give you a problem, you can sort of, and it's easy to check a solution. What you can do is sort of write a formula a polynomial size formula that says if that can sort of express that there is a solution, right? If the solution can be checked in polynomial time, then you can sort of write a poly-size formula. That's a bit hard to see. Now, there are other problems which are in here, which are actually more powerful, okay? Well, they seem more powerful at first. For example, there's something called integer linear programming, where you are actually allowed to count. You're actually allowed to say, okay, you can have, you can say, okay, x1 is 1 or 0, x2 is 1 or 0, and then you can say x1 plus x2 plus x3 plus x4 plus all of these is at least k. So it seems easier to constructivist school, possibly a relative. He was, I believe, Russian. I will check. I'm not actually, I know nothing about Satan, the person. Okay. So you think, okay, SAT seems powerful. Now, integer linear programming seems more powerful because it's easier to express, like the clique is of size k. You just say, okay, this variable is 1 if it's in the clique, it's 0 if it's not. You express these inequalities that say you can't have two things which don't have an edge between them. They can't both be 1. And then you say, okay, and then if you sum up all the variables, it's at least k. That's easier. So you want to think about what would be like a really powerful sounding problem. Like this, the class of stuff that can be added to this graph and reduced such that SAT can be turned into the stuff, and the stuff can be turned into SAT is sort of equivalent to SAT. So this is sort of like the class of stuff equivalent to SAT. If you can solve one of them, you can solve SAT. If you can solve SAT, you can solve one of them. You can solve the rest of them. But that's like, we want something meaty. So suppose that now this is going to sound like a really, really powerful problem. Okay. I'm going to give you a program. So I don't know, what are we going to call it? We're going to call this input, I don't know, input checker. Is this timer running? Yes. Okay. Input checker. Now, this is going to sound like a really, really powerful problem. Input checker is given a program. Let's say it's a C program because C is awesome. Of n characters. And a time bound. Let's say it's polynomial in n. I'm not sure if it makes sense to say that, but okay, let's say, and you're given a program and a time bound t. Okay, so this is an instance. You're given a C program, you're given a time bound t. Let's say the C program is called P. Does P stop and say yes in time t? Okay, now maybe I'm going to edit this a little bit for the course notes. Does this sound like a really powerful problem? Right? If you could solve this if you could solve this in time polynomial in n, yeah, it is, but it has a bound. It has a time bound. So this is actually, Cook likes to say that there is sort of a relationship between P and NP and RE and so recursive and recursively enumerable. So this problem is hard. It's hard, but it's possible, right? Like you could do it but maybe not in polynomial time, right? But you can see that if you could do this, it would be really cool. So in fact, for any problem where you can sit down and you can think, okay, well, if you're given an instance of the problem and somebody gave you a solution and said, just check it, and you could write a little algorithm to check it, then if you could solve, suppose that for problem A, you can check a solution in polytime. Right? Then what does it mean? Like you could check it? Well, we're computer scientists. To us, that means you could write a program to check it. Right? And since we believe that C is amazing, you could write a C program to check it. So if somebody gives you an instance, you can write, if somebody gives you the solution for A, you can write a C program. But that means to check it. And that means if you take your C program that checks solutions for A, right, you can work out how long it's going to take for instance A to check a solution. You can, if it's polynomial time, T is going to be polynomial. So you're going to say, okay, if you could do this problem, if you could solve this in polynomial time, then you could solve A, right? Because you would just take, you can check a solution. We're going to replace that by, you can write a program, a C program, that checks solutions in polytime. So suppose you can write a C program that checks solutions in polytime. Okay, so what you're going to do, given an instance of A, you turn it into a program. That's going to take polynomial time, right? We hope that the program to check, if you can check it in polynomial time, that means you can write the program in polynomial time. The program is polynomial size. And then the program, you can work out the time bound that the program is going to need. Yeah, it's not as hard as the halting problem. Like the halting problem, you could, this is the important thing. An important thing. If you had the halting problem, you could reduce SAT, you could reduce clique to the halting problem, but not the other way around. So the halting problem is not in NP because it's too hard. So this is so people like to say, okay, how do you show that a problem is NP complete? You show that it's in NP. That means it reduces to SAT. This is usually the easy step. And you show that you can reduce some other polynomial NP complete problem to it. So halting, you can reduce any of these problems to halting, but you can't reduce halting the other way. So it's not in this sort of equivalence class. Okay. So, but we're doing Cook's theorem right now. Okay. So Cook's theorem, if I told you, believe me that input checker is a powerful problem. Okay. If we could solve input checker in polynomial time, so you give me a program, you give me a time bound, and you say, okay, does this program, size of this program, if I can tell whether it stops in a given amount of time, in time polynomial and the size of the instance, then I can solve a lot of problems. Maybe T has to be polynomial. Okay, I'll think about this for the lecture notes. Okay, you believe me that that if I could solve input checker, if I could solve input checker in polynomial time, I could solve in polynomial time all of the problems for which we can check a solution in poly time. It would mean that you can then find the solution in poly time. So if there exists a polynomial time algorithm for input checker, given the program, tell if there is an input that makes it say yes, then any problem, and if we can solve that in poly time, for any problem where you can write it, you can check it, then you can solve it. Okay? Do you believe it? Do you see that this is like, it's not that surprising? I mean, look, it's super powerful. Okay, I'm just gonna have to trust that people are listening and believe me. I'm down to 15 people. Okay. So somewhere, I'm going to draw this here. I'm going to draw input checker here. Does P stop? Let's say program. Oh, sorry. This is, I made it sound too much like the halting problem. I need more sleep. Is there an input to P such that it stops? And says yes in time t. Okay, now this is okay, right? Yeah, otherwise you would just run the program. Sorry, I shouldn't have stayed up working on that problem. Okay, so yeah, that's why it's called input checker. Sorry. So you can look at it and say, is there some input that makes it say yes? Well, okay, if you have for colorability, you write a little program that, given a graph, you write a little program that checks whether a coloring assignment, a color assignment to the vertices of that graph, it just checks, is that a for coloring? So for that graph, you have a little program. And you just say, okay, is there an input? And it checks an input. And you say, is there an input that makes it say yes? There is an input that makes it say yes if and only if there is a for color. Okay, sorry. So you believe that this is a hard problem. If we could solve this, we could solve all of these. So I'm going to say input checker, obviously SAT reduces to this, clique reduces to this, other stuff reduces to hand path reduces, all of these things. Okay. All of these things reduce everything, all problems, not the halting problem. A halting problem doesn't reduce the input checker. But all of the problems for which we can check a solution in polynomial time reduce the input checker. If we could solve input checker, we could solve all of these. Okay, now Cook's theorem is Cook's theorem says sort of input checker. So Cook's theorem. Reduces to SAT. Okay? We do not have a lot of time. Okay. So do you see that all of this stuff reduces to input checker? If I can draw this arrow, then it means SAT. If I can solve SAT, I can solve all of these problems. If I can solve SAT in polynomial time, I can solve all of these problems for which I can check a solution in polynomial time, because we believe that for input checker. So if we reduce input checker to SAT, then we're done. Okay, then SAT is NP complete. It's everything for which you can check a solution in polynomial time. If you can answer SAT, you can answer those problems, all of them. And that means if you can answer four colorability, you can answer SAT, so you can answer all of these problems. Okay. Now, what we're gonna, I was trying to think of exactly how to phrase all of this. And then I managed to go and get it wrong. Okay. So we sort of know how a computer works, right? I mean, you've got these registers and stuff like that, and so you have some memory. Let's pretend that the memory is, you're allowed to use polynomial memory. So given an instance, you're allowed to like malloc some huge amount, polynomial amount of memory. And then you're allowed to run in polynomial time. So what we're going to want to do is write. So you have the program has to run in some time bound. And you want to write a formula that's satisfiable if and only if there's an input to this program that makes it say yes. People following? 14 people. Okay. So this is the reduction. The idea is to reduce input checker to SAT. Given some program, we want to write a big formula, but polynomial size, and it's going to say it's going to be satisfiable if and only if the program runs on, for some input, the program is going to run and say yes in polynomial. Now, what you're going to do is for every bit in the memory, so you have polynomial memory. For every bit in the memory, you're going to have, actually, you're not just going to have one variable. For every bit in the memory and for every time step, you're going to have a variable xij if bit I is 1 at time step j. Okay. And then what you're going to do is imagine that you have like your little control unit, your CPU. Okay. So, and you have this polynomial size memory. If the CPU is looking at, well, let's say the CPU is not looking at a bit, then if the CPU, so you have some pointer which is saying what the CPU is looking at right at the moment. If it's not looking at a bit, then the bit is the same in time step j+1 as it was in time step j. So you have to write a formula for every bit and every time step. You write something saying, okay, if the contents, like the pointer in the CPU is not to this memory address, then the bit is true if and only if it was true on the last time step. Okay, it didn't change. And then you say, okay, if the CPU is looking at some word, machine word, And then you have to go through and say, okay, what can the CPU can be doing? So, you know, you have the contents of contents of the address register, contents of the decoder, blah, blah, blah. Like however your CPU is built, so you can sort of think of it as like a little finite state machine, but you know, except it has these registers. But it's like finite memory. So, you know, you have this model and says, okay, this word is storing what other word I'm looking at, and if this is you have the bits in this, and you set all of them. This is hugely annoying. Okay, like you'd never actually want to do this. But you can think about it as like our computers are just circuits. Like and circuits are equivalent to Boolean formulas. So you could actually build a circuit that's it's only going to touch polynomial space. And it's gonna compute the contents of every bit for every time step. And so how big is it going to be? Well, it's going to be polynomial time steps, polynomial bits. It's all going to be polynomial. So yes, you could write a big formula that is true, that sort of simulates that takes, and then you say, okay, and then you have the input bits, the contents of the initial contents of memory. And you say, is there some initial contents of this input string that makes the formula true? Well, yes, if and only if you can set these variables, you can set these variables to make the formula true, if and only if you can set the bits in the input so that the program is going to accept. Okay, that's the informal version. It can be made formal. Okay, we don't have a lot of time, so do people sort of get this? I hope it'll be better in the lecture notes. So yeah, the idea is your program is only going to run, if it's going to run in polynomial time, it can't touch more than the same amount of the polynomial memory. So you can describe sort of the contents of that memory and all the time steps with a big formula that says it behaves properly. Your program executes like this. And the formula is going to describe how the program executes. Now, so that's Cook's theorem, is saying input checker reduces to set. Okay, so that means all of these problems, if you can solve any of these, any problem for which you can check a solution in polynomial time, you can find a solution polynomial if you can solve any of these. We don't think that's true. We think probably you can't solve any of these in polynomial time. But we can't prove it. Right? So it's been open now for 50 years. And this is like considered one of the 7 big problems. I mean, some of them are now closed, but in the year 2000, this was considered one of the 7 big problems of mathematics. Remember I was going about Hilbert and the problems for the 20th century. There were 7 problems chosen for the 21st century, and this was one of them. It's like, okay, are any of these actually possible in polynomial time? And so actually the question asks for proof that they're not, because nobody really thinks they are, although until there's a proof. Okay, so I wish I could do that. I wish I were doing this more formally, but I should have slept. Okay, just in the last 15 minutes, I'd like to talk about Turing machines. Okay. Because usually, so Cook's theorem is actually about Turing machines, because everybody uses Turing machines. So he doesn't talk about C programs. He talks about, does the Turing machine halt? Is there an input for the Turing machine such that it will halt and accept in polynomial time, blah, blah, blah. But C programs. I mean, you've seen them, even if you don't program in C, but you may not really be familiar with Turing machines because you've probably never seen one. And a lot of people have probably never written a program for one. So there's a reason for that, which is Turing machines became popular because back when Turing did this stuff, we didn't have we certainly didn't have electronic computers. We didn't really have we didn't have electronic computers. We didn't have mechanical computers, really, sort of this-ish. So he was, if you've seen The Imitation Game, yes, he was helping build an electronic computer. So most people had never seen a machine that did computations. So if you said computer, it was a person, okay? Like in that movie Hidden Figures, if you said calculator back then, it was a person. The people who did the calculations that sent people to the moon, sent people in orbit, wherever. So in order to talk about like what a computer could and couldn't do, you had to come up with a formal model of what is a computer. I think it's where Turing came up with the notion of the Turing test. It actually talks about like, okay, well, what if people have like extrasensory perception? How could a computer compete with that? Okay, so he was really trying to cover sort of all the bases. Oh, cool. So because he wanted to say there are certain things that computers cannot do, which we'll see at the end of the course in the diagonalization and the halting problem and Kolmogorov complexity, all that kind of stuff. But he wanted to prove that there are things that computers can't do. In order to prove what a computer can't do something, you have to know what a computer is. So you have to come up, in order for people to accept your proof, they have to believe in your definition of a computer. Because actually there was something which is equivalent to Turing machines, which is Church's lambda calculus, and that really wasn't as widely accepted until Turing came along and did Turing machines, and people said, yeah, okay, if it can be computed, it can be computed by one of these things. And I have 15 minutes. So why? But you have grown up with computers. I am talking to you on a computer. You have computers sitting in front of you. You have them like in your pocket. You have them on your wrist. You're surrounded by computers. It's not like this is 100 years ago where you don't have an idea of what a computer can do. You believe me that if I can't do something in C, then it's probably hard, right? If I can't write a C program to do something, then it's, you sort of, yeah, okay, it seems like a computer probably can't do that. You don't think like, well, maybe there's a more powerful programming language, or maybe there's a more powerful computer architecture or something like that. Yeah, okay. You'll just sort of, for third year, this is enough. You believe me that if it can't do it in C, that's a pretty strong statement. So, but Turing had to say, okay, what does it mean to compute? So he said, imagine a little person. They've got a desk. They have a pile of papers. And what can they do? So this paper is squared papers because we're mathematicians, and they can, or actually you think, well, okay, you can take the paper and cut it and make a big ribbon. Okay, so it's infinite in both directions. You have squares, and you have a pencil with an eraser, and in each cell you can write a symbol. You can erase the current symbol, and you can write a symbol from some fixed alphabet. So like 1, 0, hash, something like that. So it's fixed. It can be like, it doesn't actually matter the size, because of course, if you make it 5 times larger, well, I can just use more cells to represent. I can still use like binary, and just like if I want 256 characters, I can just use binary and make it 8 bits, except I need a hash. So it doesn't really matter what the alphabet size is, as long as it's not unary or something silly. And he said, okay, so what can this person do? Well, they can erase, they can write, and they have some sort of finite state control. Like they have a finite amount of memory in their head, right? So what you can think of is you believe in what a computer, like what a computer is. Imagine that you had a computer with some fixed amount of memory, possibly large. I mean, 2 to the 64 bytes, right? So how much is that? 2 to the 64 times 8 is very big. So it's 2 to the 67 bits, but it's finite. Now, it's not connected to the internet or anything like that. What it has is a tape drive. If you've ever seen a tape drive, I think people still probably don't use them anymore. And so what it can do, it can view a little cell on a tape, and it can, this is actually plausible, it can change it from a 1 to a 0. It's, I think they still use these big platter, they used to. I've seen them. Probably not anymore. So you think, okay, what can it do? It can read, and then if it runs, if the tape, it can run the tape forward or it can run the tape backwards. And if the tape sort of runs out at one end, then somebody comes in and changes that. Okay, what can it compute? Well, you think, okay, it's a finite state control. It's got a finite amount of memory, a lot, but it's finite, and it's got this tape that's infinite in both directions, because whenever it runs out, somebody comes in and puts a new tape on, or when it gets in it, if it's an old tape, then they sort of have a stack of like, okay, this is the ones on this side, this is the ones on this side. What can it compute? Why do we need this model? We don't anymore. But it's people, if people say Turing machines and you say, I have no idea what you're talking about, and they'll be, oh, you didn't study theoretical computer science. You can use C. I mean, we can actually show that, sort of whatever you can do with C, apart from the fact that C has like bound pointers, but if you can deal with large pointers and stuff, and C can do anything a Turing machine can do. How do you know that? You can program a Turing machine in C. So how do you actually think about a Turing machine? Well, you have this tape, and it's a finite, it looks like you've seen finite state machines, but for every arrow, so for every state, you say, I'm in state whatever. I think it's a quintuple. What state are you in? If you see this symbol, what do you do to the tape? You change that symbol. Do you move left or right? Okay, and which state do you go to? So it's like you've seen transition functions for finite state automata. So this is a bit more, normally for a transition function for finite state automata, you just say, okay, if you're in this state and you see which character, which state do you go to? This one is saying, if you're in this state and you see this character, what do you write? And do you move the tape left or right? Or do you leave it in the same position? And which state do you go to? Okay. I'm not going to make you program Turing machines. People made me do that, but I think it was a waste of time. So you can see, instead of input checker with a C program, you could do input checker with a Turing machine. Right? What do you have? You have a variable that says, okay, in step whatever, I'm in state this. In step whatever, cell whatever on the tape is a 1, cell whatever on the tape is a 0. Right? It's the same. So that was really quickly. Satan's transform will be in the lecture notes. This will all be in the lecture notes once I get this paper out of the way, and some other stuff that I have to do. The key thing is this, you see that input checker is very powerful, and Cook's theorem says that input checker can be reduced to SAT, and the idea is to show that something else is also in this class. Now we get to the point where I tell you why nobody ever sees those, like, oh, can you reduce clique to SAT? Yes, of course, nobody reduces clique to SAT. Okay. Why? Because to show that something's in NP, I wanted you to see that you could reduce it to SAT to sort of get the feeling of how to write a formula that says, that sort of expresses a problem, that says this problem can be, this formula is satisfiable if and only if this problem can be solved. Because that's really the essence of Cook's theorem. Once you sort of know, you can see that, yeah, I can write a program that's understand that SAT is that powerful. But if somebody gives you a problem, somebody said us some problem. Okay, like 3-person canoes. Okay, I mentioned that on one of the assignments of the midterm, you have this thing about putting 2 people in canoes, and you could do that. And I think I mentioned somewhere that if you can fit 3 people in a canoe, so not everybody needs to row, then the problem is NP hard. It's actually NP complete. 3-person canoes. So given a bunch of people and how much their equipment weighs, how many canoes do you need if you can put 3 people in a canoe? Okay, so this is actually a problem called 3-partition. To show that it's in NP. Before we were reducing it to SAT, but now we just have to reduce it to input checker, which means we just have to say, can we check a solution in polynomial time? So that means if we can check a solution in polynomial time, then it reduces to input checker. So it's at most as powerful of these. I mean, some problems like sorting. Sorting, you can reduce the input check. Well, okay, sorting is not a search problem, is not a decision problem. I don't know, minimum spanning trees. You're given a graph and some integer k, and you're asked, does this have a minimum spanning tree with a cost of most k? Right? That can be reduced to input checker. Clearly, you can check. Like, ooh, is there an input? Yeah, somebody gives you a spanning tree. You can check if it has the most desired cost. So there are things which reduce the input checker, which are not sort of equivalent to these in that we can solve minimum spanning trees in polynomial time, but it doesn't mean that we can solve SAT. So what we've got is 3-person canoes, and then we have to choose one of these other problems. Like suppose, I don't think you actually do this reduction, but suppose you could take vertex cover and show that vertex cover reduces to 3-person canoes. Then be like, yeah, okay, then 3-person canoes is NP complete. So it's sort of equivalent to all of these. So now you can forget about, except for maybe the midterm or something like that, you can forget about how to reduce, how to take a problem and turn it into a SAT formula. Because people don't do that, they just say, oh, is it in NP? Is it possible to check a solution in polynomial time? But to understand Cook's formula, to understand Cook's theorem, I think it's useful to see first that you can reduce things to SAT, to practice a couple of them, and then say, okay, well, you can reduce this insanely powerful thing to SAT. So now you don't have to reduce things to SAT, you just reduce them to this insanely powerful problem, and that reduces to SAT. So yeah, everything for which you can check the solution is reduces to SAT. Probably I'm down to 12 people, but I still have 4 minutes. Are there any questions? This is going to be fun to write as lecture notes. So, I mean, so yeah, like Cook's theorem, like SAT is NP complete. And this thing about everyone says like, how do you show that something's NP complete? Ooh, you have to show that it's in NP. People frequently forget to show that it's in NP. It's like, yeah, okay, you have to show, if you think about it as being like part of this, how do you show that 3-person canoes is sort of in this equivalence class? Well, you have to be able to get from 3-person canoes to one of these. And it's usually this one. You can check it. Well, it's always this one. You can check it in polynomial time if you're given a solution, and then you have to get an arrow from one of the others going here. And there are hundreds of other problems. So it's really useful if I can get it out before the midterm, which is next week. Next week. So yeah, I'm going to try to get it done this week, but I owe some administrative stuff. I owe this paper. Sorry about messing up this. Like, is there an input to P? Yeah, that's the important thing. So you have to be, it's easy as you do that. I'm going to, as soon as possible, but that's may not be super soon, but in the next few days, I hope. I know what I want them to say. I just haven't got time to sit down and type. It's supposed to rain for the rest of the week, but they've been saying that for days. So every day I think, oh, it's going to rain. I don't want to go outside then, and I'll get it's 5th of July. What's 5th of July? Yeah, the midterm starts on the 5th of July and ends on the Friday. So it'll be 5 questions again. Probably 3 dynamic programming and 2 NP completeness. Okay, we have less than a minute left. I'm going to stop this recording. Stop recording. Ding.